to take a question here that is like the ones you have, but isn't exactly the same as the ones you have, so you can still practice. So this is, if you want to find it and sort of write on it yourself, this is from May, June 2018, and it's version 41. It's not one that I've set you. Don't forget, if you want looking for more examples to do that I haven't set you, you can always do ones from papers 2016, 17, 18 or 19. I've given you the pack of the 19, so let's go through. So it says here, an X-ray beam is used to produce an image of a model of a thumb. A parallel beam of X-ray radiation, so there's that word parallel, of intensity I0 is incident on the model. So it's a model of it, but the idea is that this here is flesh, that's bone, and that's flesh again. Of course, this is a square, whereas a thumb would be different, but it would be, well, thumb shaped. So let's take a look at the attenuation data here. So it says here that the absorption coefficient mu in bone and in soft tissue are shown. As you'd expect, look, it attenuates by much more in the bone than it does in the soft tissue. So it says calculate in terms of the incident intensity I0 of the X-ray beam, the intensity of the beam after passing through. So just talking through it qualitatively, I know that it's going to reduce by an amount between here and here, and then it's going to reduce a whole lot more through this section where it's bone, and then it will continue to reduce, but it will reduce less through here. Now, what isn't obvious when you see this is you might be thinking, right, well, first I need to work out how it attenuates from here to here, and find out what the intensity is here, and then do another bit for that, and then another bit for this. But actually you can treat it as if you're going through, well, let's do it right here, 2.8 minus 1.3 to find out just the distance through the muscle. So that is okay to do that. So I'm going to, I'll show that as we go. And what it says here is calculate in terms of the incident intensity I0. In other words, you're not necessarily going to get a number here. It's going to be a kind of a multiple of I0. So how much less of I0 is it? Of course, it's going to be less. It can't, if you get a value that's, you know, a whole number or an integer number or greater than one integer number, then something must have gone wrong, because it's got to have got less. Looking here, look at the units we've got per centimetre here, as we said before. So it says, first of all, this is the easier part of the question. It's just substituting in, but you do need to know that equation. So it says calculate in terms of I0, the X-ray beam, the intensity of the beam after passing through a thickness of 2.8 centimetres of soft tissue. So that's like as if the X-ray were just going through this edge here instead of all the way through the whole thing. So of course I go through the usual things. I say I equals I0 e to the minus mu x. Always write the equation, even if you're just learning it, because you've got to stay in the practice of doing that. So now I'm just substituting in the values. That is soft tissue, so I'll be doing I equals I0 multiplied by e to the power minus 0.9 multiplied by 2.8. Now I can say that this is in centimetres because this coefficient is in per centimetre. If it were in per metre, I'd have to convert this, but I don't have to in this case because of the units I've been given. So now I can just calculate my value. So it'll be I0 e to the power, and I'll do that multiplication. Let me pause and get a calculator. I'm back with the calculator. So usually we've got the shift on the natural logarithm key here. So there we go. And you open my brackets, minus 0.9 multiplied by 2.8, because those units that go together, I can do that. That gives me a value of 0.0 80 I0. So it's this much times that. And that it's going to be to two significant figures because those are both the two significant figures. So that's the first one. So 0.080 times I0. So I don't have a value. Well, I've got the I0 there, so I didn't have to write that. It's just there. And that'll probably be my 2 marks. Let's find the next part of the question. Now it says the bone and soft tissue is shown in figure 12.1. So now I'm going all the way through. So I'll just have that on the side and I can bring it backwards and forwards. So I'm imagining it now as if it is this. I've got 2 bits here and I'm going to do I'm imagining what happens right here. It's I0 and then it's going to attenuate down to a new value which is going to be my new I0 for this section, if you like. Okay, so first of all I'm modelling this picture by saying I'm going through all this muscle and this muscle, I'm adding it together. So I'm going to do 2.8 minus 1.3. So this distance is going to be 2.8 minus 1.3. So that's obviously 1.5 centimetres. So that's I'm going to work out how that would attenuate through there. And then from here to here, that is 1.3 centimetres. That represents the bone. So I'm using my first value to find this bit here. It's like me saying, what is the value at this point here? So let's figure that bit out. So that equals I0 e to the minus mu x, and I'm going to substitute in, of course, e to the minus 0. Well, let's put it all in. 0.9 times this time 1.5, like that. That's what that value will be there. So now I'm going to use that as my starting value for the attenuation that happens here. So I'm still substituting it in to I equals I0 e to the minus mu x, but this time my I0 is all of that. So it will be I0 e to the minus, and I'm just going to leave it as it is at the moment, times 1.5. That's my I0 of this new equation. And now I'm going to do multiplied by e to the power minus, and I've got 3.0 this time from the table, times 1.3. So I'll simplify that. I'll get my calculator out and figure out what those bits are. So I haven't got any more I0s. That's the first one's enough. So I can do 0.9. So it's so minus 0.9 times 1.5 equals. Did I get that right? Well, in actual fact, let's not do all of that. You should know with your powers that if I'm multiplying these two things together, if I had x squared times x squared, then you know it'd be x to the power 4. So this time I'm just going to, and what did I do though? I added them up. So if I had x squared times x cubed, it would be x to the power 5. So this time I'm going to do e times minus 0.9 times 1.5 plus minus 3.0 times 1.3. So I think we'll probably need some extra space to do all of that. Can I just bring that down to the bottom? I'm going over here. So I now got I0 e to the power. Let me just do the whole lot all in one. So I'll do it on the calculator so you can see what I'm doing. I've got open brackets, minus 0.9 times 1.5, close brackets, plus, because I'm adding those powers together, minus 3.0 times 1.3, close brackets, equals to the minus 5.25. So let's put that down there. I'll just put it here. Equals I0 times e to the power minus 5.25. But of course, e to the power 5 minus 5.25 has a value. So let's find out what it is. So I'm just going to do my usual shift on natural log there. Hopefully you can see this. And I'll just put minus 5.25. That gives me a value of, oh, have I got that right? Let's see. I think I do have it right. So I'm going to change that into more sensible numbers. I'll actually move that across. It'll be 0.0052 because it's let me write that out. 5.248 times 10 to the minus 3, I0, like that. So that's 0.0052, because we're on two significant figures, remember, I0, and that is the end.